Welcome to Visual Algebra Lecture 3.2, Examples of Subgroup Lattices. Last time, we learned about subgroup lattices. This time, we'll see a bunch of examples, starting with all 5 groups of order 8, and then all 5 groups of order 12. Then, we'll see a dozen or so others, mostly of groups that we'll get to know well throughout the course. Some of these will be paired with a preview of an important future concept, such as semidirect products, the isomorphism theorems, or Sylow theory. This is only meant to be a teaser, because all of these and many others will be revisited later in the course. It just helps to, in the beginning, see what's out there and what to get excited about. I think you'll really enjoy this, so let's get started. Let's start this lecture with a quick refresher of what a lattice is. This slide was taken directly from the previous lecture, so I will refer you to that for more details. A lattice is a partially ordered set such that every pair of elements, x and y, has a unique supremum, or least upper bound, and infimum, or greatest lower bound. Examples that we are familiar with are subset, or Boolean lattices, and divisor lattices. In this lecture, we'll see lots of examples of subgroup lattices. So the partially ordered set consists of all subgroups of a group, and if we have h and k, then their infimum, or greatest lower bound, is the intersection. This is the largest group contained in both. And the supremum is the smallest group that contains both. That's not the union, because the union of two subgroups isn't usually a subgroup, but it's a subgroup generated by the elements in h and k, or equivalently generated by the union of h and k. Last time, we saw the subgroup lattices of both groups of order 4 and both groups of order 6. Let's go up to the groups of order 8. We'll start with D4. The first thing to do is figure out what the subgroups are. So of course, there's the entire group and the trivial group. And then there are 4 subgroups generated by reflections. All of these have order 2. There's one subgroup generated by a 180-degree rotation. That's r squared. And there's one subgroup generated by a 90-degree rotation, which is cyclic of order 4. It can be generated by r or r cubed. So these are all of the cyclic subgroups. All 8 elements generate one of these subgroups. But here there are actually some non-cyclic subgroups. So there are 2 subgroups isomorphic to V4. One's generated by r squared and f, and the other one is generated by r squared and rf. So to think about what these things mean in terms of symmetries, one of them is generated by the reflections across the side bisecting axes, and the other one is generated by the reflections across the angle bisecting axes. So here is a picture of all the axes. Here's a Cayley graph. We've seen that before. Here's a cycle graph. And here is the subgroup lattice. So it should not be obvious from this list how to put these together to make sure that everything, all the lines are correct and they're not terribly crossing each other. But once you look at it, you can see, okay, yeah, here are the 5 order 2 subgroups. Here are the 2 reflections across the side bisecting axes. Over here are the 2 reflections across the angle bisecting axes. This is the 180 rotation. Here are the 2 Klein 4 subgroups, and here's the cyclic subgroup of order 4. Here's another way to see the subgroup lattice of D4. It's the same picture as before, but now I've just decorated each of the subgroups with a cycle graph where I've colored in exactly which elements are in the subgroup. So I'm going to move on, but I encourage you to pause this and spend a few minutes, or maybe not a few minutes, maybe 1 minute looking at this and thinking about it. What do you notice about the similarities of these subgroups versus these versus this one, for example? Here's another way to see the subgroup lattice of D4. I think it's fairly self-explanatory. Here we have all 8 symmetries up here. Here we only have the rotations. Here we have this Klein 4 subgroup and another Klein 4 subgroup. Here we have the 180 rotation, And here we have the 4 subgroups generated by a single reflection. Let's do the quaternion group Q8 next. The first thing to do is to determine all subgroups. And a good place to start, as usual, is to see what the cyclic subgroups are. So every element generates a cyclic subgroup. 1 generates a trivial subgroup, -1 generates a size 2 subgroup, and then the other 6 elements, I, j, and k, and their negatives, all generate an order 4 subgroup. And clearly, I and -I generate the same 4 elements, and similarly with j and k. So these are the cyclic subgroups, but I claim that these are all of them. There are no other proper subgroups. So see why, let's see, what can we add to these subgroups to get something bigger? Well, if I have these 4 elements, and I add j, or -j, I'm going to get k, and then I'll get everything. Similarly, I can't add k to this. Over here, I can add things to it. If I add I, well, I get these 4. J, I get these 4 elements, and so forth. So there's no other subgroups besides these. So here's a Cayley graph. Here's the cycle graph. Remember, there's all these size 4 cycles. Well, there's 3 of them, I guess. And here's the subgroup lattice. So here are the order 4 cyclic subgroups, and they all contain the subgroup generated by -1. One thing I want you to notice is, what does this remind you of? This little diamond shape. That's the subgroup lattice of V4. We'll come back to that. Think about why that might be appearing at the top of this subgroup lattice. Let's move on to the abelian groups of order 8, starting with Z2 cross Z2 cross Z2. So there are 7 non-identity elements in this group, and thus 7 choose 2, or 21 pairs of non-identity elements. Each of those generates a subgroup isomorphic to V4. But this triple counts all such subgroups, because we know that V4 consists of 3 elements, call them E, V, H, and VH, or R. And this is generated by any 2 of them, so VH, VR, or HR. In other words, these 21 pairs only make up 7 distinct groups. So in summary, we have the entire group G, the trivial group, 7 subgroups isomorphic to C2, each one generated by a non-identity element, and then 7 subgroups isomorphic to V4. Here's what that subgroup lattice looks like. All 7 of these are Klein 4 subgroups, you'll note. And then next to it, this is the subgroup lattice of the cyclic group Z8. We proved in the previous lecture that all subgroups of a cyclic group are cyclic, so we don't even have to bother looking for anything else. So Z8 is generated by 1, by 3, everything relatively prime to it, so that's 5 and 7. The subgroup generated by 2, that's just the even numbers. That's also generated by 6, and then that's it. Note that we have every number appearing here once. 0, 1, 2, 3, 4, 5, 6, and 7. So this group has 16 subgroups. This one just has 4. Let's make a quick remark. We've seen the subgroup lattices of 4 of the 5 groups of order 8. D4 has 5 elements of order 2 and has 10 subgroups. Q8 has only 1 element of order 2, and it only had 6 subgroups. And Z8 also had 1 element of order 2 and 4 subgroups. Whereas Z2 cross Z2 cross Z2 has 7 elements of order 2 and 16 subgroups. As a general rule of thumb, groups with elements of small order tend to have more subgroups than those with elements of large order. The following Cayley graphs show 3 different subgroups of order 4 in Z2 cross Z2 cross Z2. So this one is a subgraph of the Cayley graph. This one here is not, or at least it's not an induced subgraph. And at least these 4 sit along a plane, whereas these 4 nodes don't sit along a plane. So I encourage you to look for the other 4 Klein 4 subgroups in this Cayley graph as well. There is one more group of order 8 whose subgroup lattice we have not yet seen, and that is Z4 cross Z2. So here's a Cayley graph, and here's the subgroup lattice. So let's think about where these subgroups lie in here. So there's 3 order 2 subgroups generated by 0, 1, 2, 1, and 2, 0. And there's a Klein 4 subgroup consisting of these 4 elements. And there's 2 cyclic subgroups of order 4. One's sitting right here, and the other one is generated by 1, 1. So it's red, blue, red, blue, red, blue, red, blue. So these 4 elements. Let's summarize the sizes of the subgroups of the groups of order 8 that we have seen, which is all of them. So here are the groups, and here's how many elements they have of each order, 1, 2, 4, and 8. And here's how many subgroups they have. So on one end of the spectrum, we have a lot of elements of large order and very few of small order. Here, this is kind of moderate. We don't have anything of order 8, but we got elements of order 4 and only 1 of order 2. Now we have more elements of order 2, and now we have even more. And over here, we don't have any elements of order 4 and 8. And notice how the number of subgroups is increasing along this direction. Several observations. The first one we already made. Groups that have more elements of small order tend to have more subgroups. But one more thing. In all of these cases, the order of each subgroup divides the order of the group. Did you notice that? Any idea why that is? Or if that's always going to hold? Well, it will, and we'll prove it in the next lecture when we get to cosets. In the meantime, let's take a tour of a whole bunch of subgroup lattices of various groups that we've seen, and a few that we have not. Now let's go exploring. First, here's Z2 cross Z6. This is one of the 5 groups of order 12. My highlighting in here, some edges being light and some being dark, is not needed, but it's just meant to showcase this duality of this Klein 4 subgroup here and this Klein 4 motif up here. We'll soon get to see that this is up here because V4 is a quotient. Here's the alternating group, A4, another one of order 12. Here are 3 different Cayley graphs, and here is the subgroup lattice. Next up is D6. Here's a Cayley graph, and here's a subgroup lattice. What do you notice here? This kind of looks like the one of Z2 cross Z6 that we just saw, right? It had that diamond up here, and well, not quite a diamond here. Like if we could collapse these subgroups into a single one of them, it would more resemble what we just saw. And that's going to be a theme, as we'll see. Here is D6 once again, and I've drawn the subgroup lattice 4 times because D6 is a semidirect product of 2 of its subgroups 3 different ways. C6 with C2, C3 with V4, and D3 with C2, and it's also a direct product of D3 with C2. And I've highlighted these subgroups in the lattice. And you'll notice something. In all of these cases, these 3 cases of semidirect products, this red subgroup, this is the A, the thing that gets rewired, it sits here and there's only one of them. And then the B subgroup that gets blown up for balloon, if you haven't watched my semidirect product lecture, please do, sits down here somewhere, and there's multiple of them. And that's not a coincidence. I'm trying to explain this without using the word normal subgroup. And then over here, when it's a direct product, both of these things are unique. You may say, well, wait a second, there's 7 of these things, but there's something different about this one than the others. You know, all of these only have 1 parent. This guy has 3 V4 parents. So it's different. This is generated by the 180 rotation. These are generated by reflections. So what you're seeing here is a way to visually spot semidirect products just by inspecting the subgroup lattice. That is an incredibly powerful technique that usually does not get mentioned because most books and most classes do not really emphasize subgroup lattices. They might have a few examples, but this is an incredibly useful skill that we will hone, and we'll be able to see all sorts of subgroup lattices and spot semidirect products. So it's really an advantage of our visual pedagogy. Here are the subgroup lattices of the 5 groups of order 12. We've seen 3 of these so far in this lecture. But what do you notice? Starting with C12. Well, what I notice is that if you start with this and you replace this C4 with the V4, and this is an informal thing when I say replace this. But if you put a V4 here, it's going to force a V4 motif to be up here as well. Like you kind of pull this apart a little bit. Now from here, if you pull this V4 apart, you get this subgroup lattice down here. And that changes things. So these C6s, 2 of them become D3s. And now you have 7 subgroups of order 2. But what else can you do? Because if you take this C3 and you pull this apart, or maybe you can do it here, you get down here. Now you lose the C6s, but you get 4 subgroups of order 3. Now if you collapse the C3, or maybe a better way to say it is if you pull apart this V4 and you get multiple subgroups of order 4, well, you get the subgroup lattice of the dicyclic group. And again, this pulling apart subgroup lattices is not a formal thing. It's just, to me, I look at these pictures and I see a lot of structural similarities. And that's not random. When we learn about the Sylow theorems, we will learn that the P subgroups, when I say P subgroups, remember that those are subgroups of order P to the n, they come in towers. So these are the 2 subgroups, that is the subgroups whose order is a power of 2, and these are the 3 subgroups, those whose order is a power of 3. And they will always come in towers, and the top of the tower is going to be conjugate, something that we'll learn shortly. And the Sylow theorems tell us how big or how many subgroups can be at the top of the tower. So there can only be 1 or 3 order 4 subgroups here, and there can be 1 or 4 order 3 subgroups. So we'll learn all about that near the end of chapter 5. Here is the dihedral group D8 and the semidihedral group SD8 and their subgroup lattices. What do you notice? Well, the dihedral group has this symmetric lattice, and then the semidihedral group, it's like you've taken away half of the bottom part of the lattice. That's one reason why I like the term semidihedral over quasi-dihedral, which is sometimes used in various books. That's one of the reasons. I also like the relationship, of course, between dihedral and semidihedral and abelian and semi-abelian that we've seen. Here is the dihedral group and the generalized quaternion group Q16. What do you notice here? So whereas the semidihedral group, we were missing this lower right half, well, for the generalized quaternion group, we're missing both bottom halves. Naturally, the generators change a little bit. So once we get rid of these subgroups, these groups now are cyclic, whereas these things were Klein 4. So we can't just copy paste and get rid of things. As we go from one group to another and certain subgroups appear and disappear, that those cause cascading changes to the other subgroups. Similarly, these 2 subgroups are both isomorphic to D4, where the corresponding subgroups over here are isomorphic to Q8. And maybe you're not familiar with that, but remember we did see the subgroup lattice of D4 earlier in this lecture, and we saw the subgroup lattice of Q8 as well as that sort of kite-shaped thing. Here is the Cayley graph and the subgroup lattice of the diquaternion group of order 16. Recall that we devoted an entire lecture to this in chapter 2. what do you notice? Well, one thing is, if you look at this subgroup and everything above it, have we seen that subgroup lattice before? Slightly rearranged, but yeah, that should look like Z2 cross Z2 cross Z2. That's not a coincidence. Turns out that the quotient of this group by that subgroup is this group. Also notice something I think I said in the lecture where we saw this, that there are multiple subgroups of order 8 that are different. So if you go around this outer ring, you get a subgroup generated by D4. Recognize that Cayley graph? Then if you, how do I want to say this? If you take the 4 nodes on the x-axis and the y-axis, you get an abelian group. So that's one of these C4 cross C2s. And then the quaternion group sits inside here as well. That consists, remember, of these 8 elements, the ones that are non-adjacent. And that's going to be this. So that's the only quaternion subgroup, but there's 3 subgroups isomorphic to D4, and then 3 that are C4 cross C2. We'll come back to this and see it in a future lecture. Here is the subgroup lattice of another generalized quaternion group, this time Q32. Doesn't it look kind of like the other one? In fact, what does this remind you of? If you take the subgroup lattice, or the motif above here, that's actually the dihedral group D8 that we saw earlier. And not surprisingly, as I've kind of hinted at, that means that this group mod this subgroup, or the quotient of this by this, which we still don't formally know what that is, we will see by the end of this chapter, is isomorphic to D8. Remember how we saw the generalized quaternion groups initially in the lecture on the dicyclic groups? I said when n is a power of 2, these have properties that the other ones do not. And then I said, in particular, every single cyclic subgroup in here, take any of these elements and any of these elements, will contain -1. Well, except for the trivial one. In particular, all of these elements of order 4, their square is -1. That's r to the 8. And because this is a power of 2, for any of these, if we multiply it together by itself, we will get to -1 before we get back to 1. And what that means is every cyclic subgroup, and let's see where those subgroups are. So all of these are cyclic subgroups generated by a single element. There are other ones, but all of those contain, on that one, -1, the subgroup generated by it. So what that means is that the subgroup lattices of the generalized quaternion groups will look like a subgroup lattice of some other group on a stick. And that other group is going to be dihedral, and it's because the generalized quaternion group is going to be a quotient, or is going to have a quotient that's isomorphic to a dihedral group. And if you quotient out by by -1, and by -1, I mean it's really that, which is just the elements plus or minus 1. Here are 2 subgroup lattices of non-abelian groups of order 20 that we have seen. If you've been watching my lectures, you'll recognize these from my Chapter 2 lecture on semidirect products intuitively. These are both semidirect products of C5 with C4 over some labeling map. And I want you to notice several things. First of all, D5 is a subgroup of this one. And I'm going to do what I did in that lecture, is I'm going to label the order of the elements. So all of these, or of some of the elements, all of these have order 5. And then down here, all of these will have order 2. And we know the dihedral group has 5 elements of order 2, if it's D5. Whereas over here, same thing in the top row, 1, 5, 5, 5, 5, and then there's a 2 here as before, but all of these elements have order 10. It's the cyclic group C10 has order 10. So there's no D5 over here. Well, there's this subgroup lattice sitting at the top of the lattice. And as I've told you, that means that, as we'll see in chapter 4, that D5 is a quotient of this group by this subgroup. I also want you to notice that this is a dicyclic group. And as I mentioned in the previous slide, the generalized quaternion groups have quotients that are dihedral. And actually, when we saw the lecture on dicyclic groups, we saw an example of that, and I said that that holds more generally. And here you can see it. So this is a quotient that's dihedral, but it's no longer a subgroup lattice on a stick like it was for the generalized quaternion group, because there are cyclic subgroups that do not contain. This is the subgroup. You can think of it as generated by -1. Go back to the lecture on dicyclic groups if you don't know why this is -1. But these cyclic subgroups do not contain it, so you have like a little bit of a protrusion. And that's one reason why the generalized quaternion groups have a similar structural property that the other dicyclic groups do not. Here is the subgroup lattice of the special linear group SL2Z3. And by now you should see motifs all over the place. So this subgroup right here has order 8, and it's isomorphic to Q8. So do you recognize this from earlier in the lecture, this little kite shape? What else do you see? Well, these elements have order 6. This is order 24. So these things are all isomorphic to C6. These are C3. This one is isomorphic to C2. And what else? You see anything else? Well, you see a little diamond here. That's not hanging from the top or sticking out of the bottom. It's something that's called a subquotient. We'll learn about that in chapter 4. But we also have this thing hanging from the top. Does that remind you of anything? We've seen that. This is the shape of a subgroup lattice of order 12. And it's actually A4. Okay, so a lot more about this group is coming. It's a great example of a solvable group that takes 3 steps to get to the bottom of the lattice, and that's something that we will briefly touch upon in chapter 4, but really focus on in chapter 6. Here's S4, the symmetric group. I couldn't resist. I had to show you as many of the Cayley graphs as I could fit in here on Archimedean solids and then on the Nauru graph as well. That's not a polytope. If you haven't seen these before, please watch my lecture on symmetric and alternating groups in chapter 2. Now, what do you notice about this? Well, I noticed several things. First of all, there aren't that many obvious motifs that are kind of hanging from the top. Well, there is one actually right here. Recognize that? Does that look like D3? Subgroup lattice of order 6, or that we saw in the previous lecture. And that's really about it. In other words, there are not that many quotients of S4, and that has to do with the fact that there's not many so-called normal subgroups. And we'll learn about what that is in the next lecture. But I see other things as well. So I see, like, it looks like it's trying to be a diamond, a Klein 4 subgroup right here, or pattern, but it's like pulled apart. There's like 3 of them, sort of, and there's one in this middle. So that's the sort of thing that when you see a lot of these things, you'll see a lot of similarities and differences and patterns that are kind of hard to explain or quantify, but they're definitely there. Here's a subgroup lattice of A5. What do you notice here? Well, one thing is that there's no obvious quotient, if you believe me about things hanging from the top. So there's there's nothing that really stands out as like a subgroup lattice of a group that we've seen. And there's a reason for that. This is what's called a simple group. It's one that cannot be collapsed any further via quotients. That's not at all obvious, but something else that I noticed is that there aren't any subgroups of size bigger than 12 other than the entire thing. Isn't that weird? I mean, this thing isn't really to scale. You know, I go 1, 2, 3, 4, 5, 6, 10, 12, and then way up to 60. So if it were to scale, it would look a little bit different. So I think this is interesting to look at, and we'll learn about these especially in chapter 6 when we study simple groups. Here's a subgroup lattice of C7 semidirect product C6, which has order 42. We'll see this, I think, a little bit later in this class, in chapter 4. It comes up as an example of a nice little theorem, and I think we'll see it in Galois theory as well. As the Galois group of a polynomial, I think x to the 7 minus 2 is this group, and there's this nice correspondence between subgroup lattices and subfield lattices. But for now, what do you notice? There's a little motif hanging from the top, and that has, not clear maybe what that is, but I claim, as we'll see, that is a copy of C6. And then that's really it. Like, this thing looks like a pulled apart version of other things. So if we could like somehow collapse this and collapse this and collapse this, maybe we might see another pattern. And again, that's just kind of the nature of subgroup lattices and how they are similar and different. Like, they often look like pulled apart or collapsed versions of each other. And then to wrap up, let's do one more of these things. This is the semidirect product of Q8 with C9. And once again, there's patterns that I see. It's like we have this little Klein 4 motif here. It's called a subquotient, and up here. And there's a reason why I've highlighted these is there's this duality that we'll learn about when we study the isomorphism theorems. That says if you have a subquotient here, you will have one here. I mean, formally, if you have a subgroup B right here, and you have a subgroup A right here, and this is the subgroup AB, and there's some condition on A and B, something about normality that I won't get into, and this is the intersection, A intersect B, then this theorem says that this motif, the subquotient, will be the same as this one, and this one will be the same, in this case, as this one. So it's a little bit of a teaser. It's called the diamond theorem because, you know, this is kind of diamond-shaped. And what else do we see? You know, we don't quite see one of these, like, up here. But, you know, again, if we could collapse this a little bit, you know, that shape looks a little sort of familiar. Well, actually, not really. I'm going to correct that. I'm going to say this shape looks a little familiar. Do you recognize that? What is that? That is the shape of the subgroup lattice of A4 of order 12. We've seen that a few times in this lecture. What is this? What is this? Things to think about. I don't think we've seen those lattices. And that is a good place to stop. In the next lecture, we'll learn about cosets. This is another structural feature of groups. It has to do with the fact that a Cayley graph has this regularity property, and every little piece looks like every other piece. And some of those pieces are subgroups, and some of those pieces are cosets. And that's a tool that we'll need to define the concept of a normal subgroup, which is one of the most important definitions in this class. We'll need that before we can talk about quotients. Okay, so there's a lot of fun stuff coming up with a lot of pictures. Stay with us.